Unit 3 is in two parts. One part is rather short. That's what we're doing today. And I call it the qualitative part. The quantitative part will start on Monday, or not Monday, Tuesday when we get back. And it's more mathematical. Today, there'd be no numbers today at all. I'm going to talk about what is a solution, how do things dissolve in a solution, what are the factors that will change the kinetics of solution. That's what we're going to focus on today. Okay. Who knows what a solution is? Everyone's heard of a solution, right? What is it? It's like, what color is the sky? Everyone goes, blue. Why is it blue? All the hands go down. What's a solution? And what was the last part? Okay, a solution is, everyone thinks of a solution as something water-based. That's a subset of what solutions are. Solutions are any two chemicals that homogeneously mix. Homogeneous means you cannot tell the difference between one versus the other. I'll give you an example of that. Vodka. Vodka is made up of two things: ethanol, which is drinking alcohol, and water. Can you tell the difference between the water and the alcohol in there? It looks just like plain old water. Yeah, I mean, that's a good example of a solution. Sugar and water dissolving. Can you see the sugar if you didn't put in too much after it's dissolved? No, it's homogeneous. Heterogeneous is like oil and water. You can distinctly see the oil versus the water. So solutions are homogeneous. But they're not limited to liquids and solids. The air we breathe is also a solution. It's made up of nitrogen, oxygen, carbon dioxide, carbon monoxide, unfortunately. And can we see the nitrogen in the air versus the carbon dioxide? No. So they're very homogeneously mixed. And it's not a liquid unless we cool it down a lot. I mean, a lot, yeah. So uh-huh. Like, I know it's water, and there's a chemical called hydrogen peroxide. It's got two O. Let me start. I forgot to turn on the recorder. Let me turn on the record real fast there. No, it's already gone. Okay, so hydrogen peroxide. That looks like this. Now that's a liquid, but you cannot buy this at the store. You can only buy like 5% or something like that. It's very dilute with water. And this is an oxidizing agent. That means it oxidizes something. That's why it makes things white. That's why it kills bacteria. It destroys bacteria. That's why they used to put hydrogen peroxide on cuts and bruises and wounds, leaving this open. They don't do that anymore. Aaron, is that officially called off, using hydrogen peroxide on wounds, or do they still do that? No. It's okay. She's an EMT, that's why I was asking these things. Yeah, peroxide damages tissue, healthy tissue and bad tissue, yeah. Anyway, it kills germs really well. It totally messes up their cell walls. and they burst open, and you can't live if your cell walls are burst open. And it becomes the opposite of oxidation is reduction, and it's reduced. Oxidation is a transfer of electrons. So, so it's kind of a long answer. Okay. So getting back to solutions now. Um, two or more chemicals. Oh, let me do one more example. So we talked about gases solution. We talked about liquid solution, and there's one more solution that you probably want to think about. I don't have a gold ring, but if you had a gold ring, they put 5% copper in it and strengthen it. So if you were going to take a gold bar to someplace to cash it in, they would weigh it and then take 90% of that weight or mass and pay you on that. Because the other, not 5% of it is copper, and the other 5% is called profit to the dealer. But they don't give you 100% of what you bring in. Copper is added for strength reasons. Gold itself is very soft, so it wears, and you know what gold costs. We just looked it up a couple of weeks ago. It's $3,400 an ounce. So you don't want it wearing off. So they put copper in there. Copper and gold form a solution. You cannot tell the copper's there by looking at a ring. So it doesn't have to be water-based. It can be air or a gas, liquid, or solid. All of them are solutions. Solutions have two parts. A solvent, and that's the most. Something 60-40, whatever is a 60 version is the solvent. The other part is solute. Solute. And you can have two or more solutes, but only one solvent. Air. Now, one solvent, nitrogen gas. The solutes are oxygen, carbon dioxide, carbon monoxide, or whatever other gas is in there. Okay? All solutions are set up this way. So we're going to be working in this unit with water-based solutions, 100%. But by definition, it's much broader than that. Okay. All right. So let's talk about what happens when things interact. When we drop a crystal of sodium chloride, common table salt, into water, what happens? It dissolves. What does that mean? Okay, it could. Visually, what happens? Disappears. You cannot tell the salt from the water. That means it's a solution. Now, if you put a whole bunch of extra salt in, like instead of 1 teaspoon, you put in, a pint of salt, it's not going to all dissolve. That's because it's saturated. So you can only have a certain amount of solute in a solvent for it to dissolve. Now we're not going to, then there's supersaturation and all this fancy stuff. Okay, so what happens then in water with the salt? Okay, it doesn't happen instantaneously unless the water is super, super hot and you're vigorously stirring and you throw in a little bit of salt. It goes like you're going to make pasta. When you throw the salt in water, that boiling water for pasta, does it stick around very long? Not at all. It's just it's all really fast. Okay, so let's look at that now. Now, salt is called an ionic solid. That means it's made up of ions, cations and anions. There's covalent solids like diamond, graphite, very different. Ionic solids dissolve well in polar solvents. So what do I mean by polarity? We look at a periodic table. We look at a periodic table. Where's the periodic table? Let me grab a periodic table. There it is. All right. Okay. So I'm going to talk about something called a trend. And there are two parts to this trend, fluoride or fluorine and radium. Um, the trend goes that way. And there's something called electronegativity. Okay. It's a tendency for one atom to attract an adjacent atom's electrons. So fluorine has got the most electronegativity. And in Unit 4, we're going to talk about why this trend exists. And then, actually, I'm going to go to francium, not radium. And why does francium have the least? So it doesn't want electrons at all. Fluorine wants small. So in a molecule, let's look at water, for example. Those are two covalent bonds. Remember, covalent bonds are sharing electrons. However, life is not equal in the universe. Some share better than others, kind of like life. So the ones with the most electronegativity pull the electrons more than the ones with lesser electronegativity. That means we're going to form something called a polar covalent bond. Most covalent bonds are polar, 99.9% are. Pure covalent, they have to have the same electronegativity. Pure covalent. In other words, they pull the same. They each want the others, atoms, electrons the same. So it's perfectly balanced. That's why there's very few atom or molecules that have a pure covalent bond. Examples are N2, O2, H2. Those are all pure because they're the same atom, and the atoms have identical electronegativity because they're the same. So water's got two very polar covalent bonds, very polar, and they're pulling this way because oxygen has more electronegativity than hydrogen. If you look at the periodic table, here's hydrogen way over here on the top left. Fluorine is on the far right. That's pretty far from fluorine. Hence, its electronegativity, hydrogen is a lot less than oxygen. So the electrons in water want to go towards the oxygen, kind of hang around on the oxygen, as opposed to hanging around on the hydrogen. Hence, that makes that molecule lopsided in terms of electronic distribution. So we've got, and this is something that those of you who had calculus, when you get into differential equations, you'll learn about this little guy here. Actually, let me redo that. And it's short for a D. And the reason why they call them partial differentials is because this is a differential and this is a partial differential, meaning it's not as strong as a full differential. So as far as molecules go and their polarity, we're going to use the same partial again to describe polarity. So in water, we have partially negative on the oxygen end, partially positive on the hydrogen end. The reason why it's partially negative on the oxygen, more electronegativity. So it's pulling those negative electrons over towards the oxygen side. Now, for those of you who have had physics, which most of you probably haven't, there's something called a vector. This attraction is a vector. Vectors have two parts, direction and quantity. So direction and quantity. If the direction is opposed and with the other force, they cancel each other out, assuming the quantities are the same. So if we've got X going this way, then we've got Y going this way, and the quantity is the same, that means X and Y go away. It's cancel. In the case of water, they're not going 180 apart. They're angled. So part of the force is negated and the other part is not. So we basically have a net force going that way. So water basically is polar for this reason. In fact, it's very polar. Now in Unit 4, we're going to talk about intermolecular forces. This is called hydrogen bonding. When an H bonds with an O, nitrogen or fluorine, it's called hydrogen bonding. Very, very strong intermolecular forces. Okay, so there's an expression I want you to keep the rest of your life. Like dissolves like. So if we have something polar and we have something polar solvent-wise, the polar solvent will dissolve the like polar solid. Now, ionic solids are very polar. They're the most polar you can get. Salt is very polar because it's ionic solid. Water is very polar because we have an unequal vector relationship in the forces within the water. Hence, water is really good at dissolving salt, like dissolves like. Polar dissolves polar. For example, grease. I'm driving my car on a newly oiled road. I keep my car very shiny. So it really bugs me when I drive on an oily road, it gets crap all over the side of my car. I have a shiny red car that says Chem Prof on it, license plate, so you know it's mine. So do I run when I get home? Do I go and take a hose with cold water to wash it off? Why not? They're not alike. Tar or oil is very non-polar. Water is very polar. Hence, the water doesn't touch it, just beads right off. When you wax your car, by the way, it's very non-polar wax. That's why the water doesn't stick to it. So there's a way around it. What's the way around it? I'm going to get soap. Soap's called an emulsifier, a very special molecule. It's got polar and non-polar parts to it. Think of it as glue. You can glue the polar to the non-polar. You have a greasy pan, you're washing dishes. Like last night I made meatloaf. Meatloaf is not, has a lot of what I call it, fat in it. So when I make it, of course, it leaves a lot of fat residue. So when I put it in the sink with water, to clean it, I need to put something in called an emulsifier so that it glues the grease to the water. And then it'll go down the drain. Otherwise, nothing happens because they're polar versus non-polar. Surfactants are another word for emulsifiers. Surfactants make Rain-X. Anyone ever heard of Rain-X? Okay, you put it on your windshield of your car and you buff it, and it repels water. Anti-fog, that stuff we use in the lab. A couple of you, I've helped defog your glasses. That's also surfactant. It makes the water on your glasses extremely fine. So when light goes through those really tiny, tiny, tiny droplets, it doesn't refract or bend. That's why fog bends light, because there's big droplets on your glasses. Making the droplets extremely small, it refracts it a tiny, tiny, tiny bit, the point where you can't tell the difference with regular eyes. So this concept of emulsification and surfactant is very common in nature. Who's had biology in here? Okay. In general. Okay. Have you heard of a membrane, a cellular membrane? What is the purpose of a membrane? I don't mean to put you on the spot.
No, it's okay.
What is in the outside of a cell? Cell membrane. What's in the outside of a cellular nucleus? Cell membrane. Membrane. Our body is a big sack of water. All blood is mostly water. Lymphatic fluid is mostly water. Water, water, water. Muscles got a lot of water. Even fat's got water in it. So the problem our body has is how do we distinguish and keep certain reactions separate from other reactions? Something called a membrane. Water's polar, membranes are very non-polar. That's why we can separate reactions in the body by putting a membrane around the area that we want to isolate. Mitochondria. Inside the mitochondria, we produce energy. We produce adenosine triphosphate energy molecules. There's a problem, though, is how do we get things from our stomach and intestines to the cells, like fat? Is fat soluble in water? No. So our bodies have got to somehow grab the fat and move it into the polar blood and move it over to wherever we want to transport it. So it uses an emulsifier. Who's heard of HDL? LDL. Okay. High density lipoprotein. Lipo meaning fat, lipid, protein meaning, well, protein. And what happens is the protein acts as an emulsifier to move the fat around your body. That's what HDL and LDL is. Some are better than others. HDL is really good for you. LDL is, there's two kinds of LDL, and one of them is very bad for you. The other is marginal. But my point is, our body uses emulsifiers all over the place. All over the place. And there's a fancy name for membranes. It's composed of phospholipids. How's that for a mouthful? And when you take 2B, you learn all about phospholipids. You're going to be writing them out and all that stuff. One more example of an emulsifier. Is anyone in here who likes to cook ever made your own mayonnaise? How do you make mayonnaise? Okay, so we have oil and we have egg yolks. Why the egg yolk?
Egg yolk can be super red.
Mm-hmm. Well, egg yolks have a lot of fat in it. That's why it's. But there's another chemical in the egg yolk that makes that mayonnaise. Now, mayonnaise is an emulsion. It is fat suspended in water. That's why it looks like milk. Milk is white because there's fat particles in it suspended in water. So light cannot go through. There's a chemical in egg yolk called lecithin. That's the emulsifier. So if you ever making a Caesar salad, you ever made a Caesar salad, a dressing? What do you add to it? Egg yolk. That's to keep the vinegar and oil together. So it doesn't. Well, this is why. Yes. Write that down. So anyway, if you make a satay sauce, for example, satay sauces use raw egg yolk. Same thing. I was at a friend of mine's wedding, and it was a big wedding, and her boyfriend, back up, her daughter's wedding, and my friend's boyfriend was a emergency room doctor, very arrogant. Typical doctors are arrogant, and it goes, they just start. Well, he was a good example of an arrogant doctor, and he was cooking. He loved to cook, and his satay sauce broke, and there's 100 people out there expecting to have these nice skewers with satay sauce on them. So I said, well, just add an egg yolk. It's got lecithin in it. And he goes, really? How many years of school did he go through? And it was fine. Got it all mixed up. So remember that. Emulsifiers, mustard is emulsifier. What is it? Breadcrumbs, particularly Parmesan breadcrumbs are emulsifiers. And if you also want to make a quick vinaigrette, you can add a little mayonnaise. And because of the lecithin in the mayonnaise, acts as an emulsifier. Keep your vinaigrette nice and mixed. Works really well. That's why it's nice to blend industry with cooking. A lot of cool things you can do. Okay, so back to salt and water. All right, so here's our salt crystal made up of ions, sodium ion, chlorine ion, or chloride. Now what happens is we have water surrounding that crystal. And remember we talked about temperature? Temperature is the metric to measure kinetic energy of the molecular atom. At absolute zero, there's no motion at all, which is minus 273 Celsius, or 400 and something Fahrenheit. Minus now, really cold. Anything other than that, molecules are moving. So our molecules of water are moving around, all around that salt crystal. And remember, we talked about water as being partially negative, partially positive. So what happens is the negative part of the water attracts this positive sodium ion. So these form kind of a stickiness. And because the water is moving, it pulls out the sodium. With the chloride, the hydrogens now are positive, the chlorine is negative, so the hydrogens form a quasi bond with that chloride, pulls it out because again, the water's moving. And that's so this table salt is gradually pulled apart. And then what happens then is water surrounds the sodium. And the water surrounds the chloride. So though they no longer touch each other, the chloride and the sodium, because the water is in between. This is called a hydration sphere, where it surrounds cation and the anion. And that's how it pulls it out of the crystal. Okay, does that make sense on this? There's primary hydration sphere, secondary, tertiary. It just gets further and further away from the sodium and the chloride. Okay. Now, what are the factors that affect dissolving? Temperature is a good one. What else?
Being in like. Water.
Yeah, but assuming that's not going to change, that you're right. We change the polarity of the solvent, it's going to dissolve faster. Or if we lessen its polarity, it'll dissolve slower. You're right. So solvent has something to do with it. But we stick just with water, yeah. Well,
Like, you got metal, there won't be enough ion from the water to connect to the.
yeah, exactly. And that term you're talking about is called saturation. If you saturate your liquid with too much solute, like salt in this case, there's not enough water to go around. It can't get to it. So it just stays as a solid. If you have a cup of coffee and you dump in some sugar, what happens? It dissolves. How can you speed up that? Stirring it. So agitation, physical agitation speeds it up. And because it speeds it up because water is moving. Physical agitation is the same as raising its temperature. And in fact, if you had an extremely accurate thermometer, you will notice that the temperature goes up. There was a famous experiment done a couple hundred, in fact, 300 years ago, where they measured the temperature at the top of the waterfall and at the bottom. And the temperature went up as it fell, because it's more motion. Temperature went up. Okay, and there's a third factor that I'm getting at. So temperature, when you think temperature, think movement. So there's two ways to introduce movement into that: raising the temperature and physically agitating it. The third thing, if I have a crystal this big versus a crystal this big, which will dissolve faster? The little one. What if I had a pound of one big salt crystal and a pound of little ones? Which will dissolve faster? The little ones will still dissolve faster, even though the mass is the same. Why is that? Yeah.
There's more surface area, the volume.
Yes. This dissolving is done at the surface of that molecule. So it's a surface phenomenon. So if we increase the surface area, it'll dissolve faster. Okay, so a big chunk of salt versus crushed salt. In fact, our lab yesterday and today involves that same concept. We're taking the copper sulfate, we're going to grind it to finely, so the heat then affects it more because we're driving off water. And that's a surface phenomenon, same thing. So if we increase the temperature of the water, we speed the dissolving. So this means directly proportional. If one goes up, the other goes up. Inverse to that, indirect proportion, be the opposite. One goes up, the other goes down. Okay, so when we get to gases, the whole lab is on proportionality. And you're figuring out when gas changes, volume or whatever, what's the relationship? Is it direct or indirect? Yeah. Between a big crystal and powder?
Kind of the same thing. You said
Okay,
crystal and.
yeah, same thing. Okay, so small versus big. If you have a pound of the big stuff, one big crystal, and you have a pound of the little ones have more surface area. And exactly. And so this, where the water's working on pulling out the sodium and chloride ions, it's acting only on the surface. So if we increase the surface, we increase the speed at which it dissolves. So for example, in cooking, powdered sugar dissolves faster than granulated sugar. Much faster. Okay, and remember now, temperature is the metric we use to measure kinetic energy of the molecule. That's why if we stick a thermometer in our coffee that's cold by our thermometer, it's going to take longer for the sugar to dissolve. Now, we keep talking about table salt and sugar. Do you think sugar is polar or nonpolar? He says polar. Why? That's correct, by the way, but why?
Because they both dissolve.
So we're using this observation of quickly dissolving to say, well, this is polar because it acts like a polar substance. Let me show you what sugar looks in a super duper microscope. I'm going to draw glucose because that's as simple as sugar. And this is glucose. When you take 2B, you'll be able to draw this as fast as I'm drawing. Okay, what do you see in that molecule? A lot of what? OHs. Remember with water, what makes water polar? The OHs. So even though this is not ionic, it's still polar because of all the OHs. Does that make sense? The more polar parts, and in organic chemistry, we say functional groups, the more polar the functional groups, the more polar the overall molecules. So this is why sugar and water are homogeneous. It's because sugar's polar, water's polar. Ethanol. Drinking alcohol. What do you see in that ethanol? OH. That's why alcohols are very polar and hence dissolve quite nicely in water. So like dissolves like. Polar dissolves polar. Okay, on your test 3, you're going to be asked a question guaranteed. How does a sugar crystal or a salt crystal dissolve? And I want you're going to be having to draw diagrams like this on your test. Basically, in a nutshell, reproduce our lecture today. There's one more part of this lecture I want to talk about. Okay, why does salt dissolve in water and sand does not? Sand is polar. Ferguson, you just said if it's polar, it'll dissolve. That's right, it will.
Basically tiny rocks. The rocks don't fall water.
Right. Then why? You're right.
No.
Okay, there are two forces at work here. There's something called a solvating force. That's the force at which the molecule will be torn apart, whether it's ionic or whatever, from its solid form, from its crystalline form. And the other force is called crystal lattice force. Okay, so the solvating force pulls the crystal apart. The crystal lattice force keeps the crystal together. And it's a battle of two forces. So in the case of sand, the crystal lattice force is very strong. It's like the force be with you kind of deal. Solvating force is weaker when sand is in water. It's not strong enough to pull the silicone and oxygen away from the granule. In the case of salt in water, the solvating force is stronger than the crystal lattice force, so it's able to pull it apart. So if solvating force is greater than crystal lattice force, it dissolves. If the crystal lattice force is greater than the solvating force, it stays intact. Now, crystal lattice force is not affected by temperature. Solvating force is, because solvating force depends upon movement. So we can increase the movement of molecules by increasing the temperature. So if something doesn't dissolve, up its temperature and it'll finally dissolve because the movement of the solvent is increased. So solvating force is directly proportional to temperature. Temperature goes up, solvating force goes up. Temperature goes up with crystal lattice force, nothing happens. So know these forces, how they interact. One keeps it together, one pulls it apart. Oh, crystal. Abbreviation for crystal, sorry. Instead of writing out CRY, I say. Okay, so that's the qualitative side of solutions. Learned a lot of stuff today. And really interesting stuff. Next time you're with someone in a group, ask them how salt dissolves in water. Then amaze them with your knowledge. By the way, that doesn't work very well. Not that I've tried it. I used to have a neighbor from hell. She was the biggest know-it-all, and she thought she knew everything about chemistry. So I was always saying, "Oh, it's not quite true," you know. One of them was dissolving in water and emulsifiers. She thought she knew everything about emulsifiers and surfactants. Nope, sorry, but anyway. So I had to be very, oh, the way I told her she's wrong. She was an awful, oh my God. Stories I could tell you would just amaze you. How, awful a neighbor can truly be. She couldn't, well, she had really bad kidneys, so she was up, always up in the middle of the night. And my door and her door, she was directly apartment next to me. Of course, wait a minute, let me, stop the recording here. And